So let's talk about chemical kinetics. In physics, there are two main branches. One is called statics, and that's where everything just sits still and you concern yourself with opposing forces and things like that. Nothing's moving. It's like doing calculations on simple machines like levers and pulleys and things like that. Then there's kinetics, and kinetics always denotes motion. So in chemical kinetics, the type of motion we're interested in this discussion is the movement of the reaction progress itself. Like how fast is the reaction proceeding? So we need a way to measure that and quantify it and describe it. And that's what we're going to be doing today. So the reaction rate is the way we describe chemical kinetics. How fast is the reaction proceeding? You have two options. You can describe the reaction in terms of disappearance of a reactant. Like we have, you have reactants, and products. Then you can say, how fast is one of these disappearing? You can also say, how fast is one of these appearing? As it turns out, the most useful approach to chemical kinetics, not the only approach, of course, but the most useful approach is disappearance, rate of disappearance. How fast is this disappearing? What's the change of concentration of one of these components? So we say, what's the concentration at the final? The rate would be the concentration of A final at the end, and then subtract what was it to start with. And then how long did it take? What's the change in time? That's a rate. Anything that changes relative to time is a rate, or a speed, or a velocity. It's got several different names. But the rate of our reaction is like that. Now, for simplicity's sake, you know that the final concentration of A is going to be less than the initial, so the value would be negative. Right? It'd be a negative change in A over time. But sometimes we leave that negative out because if we know it's negative, then we don't need it. So you need to express the concentration of A in some useful value of some kind. And what we often do is use molarity, right? Moles per liter. So the concentration is changing during the reaction. It could be very fast. It could be moderate. It could be very, very, very slow. Slow reactions are easier to study because you have time to set up and do measurements on the way. But you can only do so many of them. If you're doing a series of experiments, you can only do so many of those in a given period of time. So you want something intermediate, or you want instrumentation that can measure these concentrations instantaneously. Then you can follow the reaction even if it's really fast. And that's what some reactions are studied now that weren't studied in the past, because now you can determine the concentrations non-destructively. And you can watch it over time very fast. Okay, so this would be a set of data that you might acquire for this particular reaction. This would be the decomposition of nitrogen dioxide. The balanced equation says 2 moles of nitrogen dioxide decompose into 1 mole of nitrogen monoxide and 2 moles of nitrogen monoxide and 1 mole of oxygen. And you can see the concentrations changing. If you start at time 0 with 0.01 molar concentration of NO2, the starting position says that there's no nitrogen monoxide and there's no oxygen. That stands to reason. This is at the very beginning of the reaction, so everything is on the reactant side. And then over time, you watch it, and you see that this one decreases, and these two start to increase. Okay, and notice that as this one decreases a certain amount, it decreases by 0.0021. Well, the ratio is 2 to 2, or 1 to 1. So as this one disappears in that amount, the exact same amount shows up over here as a reactant product. Right, so that's 1 to 1 or 2 to 2. If it's 2 to 1, like this one's 2 to 1, then what disappears over here as 0.21 shows up over here as 0.0011, which is rounded off. It would be 0.00105, but rounded off it's 1,1. So the ratios here are the same. Even during a kinetics experiment, the molar ratio of the reactants and products hasn't changed. So if so much disappears over here, the correct ratio shows up in the products. And over time, you can watch this one decrease as these increase. Okay, so that would be like a data set for this experiment. But data in a table, while useful, is difficult to visualize. I mean, you can't really see what's going on. It helps to graph it. Right, so that's what this one looks like. You got this, right, here's the amount when you start, right there, of the reactant, and these are the products. So oxygen shows up half as fast as nitrogen monoxide. That's why the curve is like this. Curve is like that. Right, so they're different by a factor of 2. And as this one decreases at a certain rate, this one increases at the same rate. Now, how do we tell the rate? Well, if you graph these things, notice that on this axis is, the y-axis is concentration, and the x-axis is time. So what's the slope of a line? That's the question. If you have a straight line, time here, concentration here. If you had a straight line, then all you would need to do is pick 2 points, right? There's one, and here's one. Right. So between those 2 points, what's the slope of that line? Remember, slope is rise over run. So it's the change in y divided by the change in x. The change in y is concentration. Change in x is time. The slope of the line is the reaction rate. So how do you get it? Well, you say, okay, what's y? Well, between here and here is the change in concentration. Okay? Between here and here is the change in time. So there you have this one divided by that one. That's the reaction rate. If you plot those numbers, the problem is, you've probably already seen it. The problem is, that's not a straight line. It's a curve. So how do you tell the slope of a curve? Okay, we need to introduce the concept of instantaneous velocity. Instantaneous velocity is an extension of this concept, only now, if you have a curve like that, the instantaneous velocity is, well, what would be the slope of the tangent at that point? Right? So the slope of this straight line is a tangent to that curve. And that is the instantaneous velocity at that point of the curve. If we measure it somewhere else, like down here, it would be different. See, it's changed. So the instantaneous velocity along that curve changes. That means in the beginning, a very steep slope means it's changing really fast relative to other places. Now, as you go down like this, it slows down. It doesn't change as fast. And here, it doesn't change as, if it changes even slower. So that's what that curve means. The velocity of the reaction is changing over time. As you lose reactant, then the speed of the disappearance of the reactant changes. The reaction rate changes. Now, this is just an example. This curve type arrangement is generally consistent for many reactions, but the size of the curve, the slope of the instantaneous velocity along the curve is different. And that's what we want to investigate next. How do we describe those differences among the reactants? Because that curve is going to be different for each reaction. Okay. So there was the instantaneous rate that I mentioned earlier. Now, if you know calculus, or you're ever going to take calculus, you'll learn how to calculate that slope from the equation of the line.
Been 20 years.
Huh?
It's been 20 years since I've touched calculus.
Okay, but maybe you remember a little bit about it, right?
I just need a refresher.
In calculus, see, the delta is an algebraic expression, right? It's like a big change. In calculus, we call it D, right? D delta concentration over dt. Remember that? The D just means an infinitesimally small change, which is required to understand the instantaneous rate at that point. So instead of delta, we use the little d. That's differential calculus. Okay, maybe it'll come back to you. It's not really important for this class, just to understand that on a curved slope, the rate actually changes over time. You might have a very high rate in the beginning, but over time, the slope of the line and the rate decrease. Okay, so the rate does change over time for some reactions, and we're gonna look at the types that do and the types that don't. Okay, so we're aiming for is not just the rate, because we know the rate changes. What we need is an expression for the reaction that will give us the rate at any point in time along that curve, right? We call that the rate law. So the rate law in general, for this reaction, well, let me use a generic reaction. The rate is equal to some constant that's characteristic of that reaction times the concentration of whatever we choose, and we're going to focus on disappearance of reactant. Whatever that concentration is at any time, raised to a power. Okay, this is the rate constant, and the units of measure for the rate constant can be, the sky's the limit. Right? It just, we don't even put the units in here until we've actually determined what they are. And then the concentration here at any particular time, whatever time you pick, the rate constant is a constant, and then N is what we call the order of that particular compound or element, the reactant. The order of the reactant is the power of that expression. Okay, so that's by way of definition. That's it. And you'll have one of those for every reaction that is studied. In this case, we're not interested in the concentration of the products. Because if we have the balanced equation and we determine something here, say we're finding the rate law for this reaction, we find a number for the N, we find a number for the K, then if we know what the rate of the reaction is at any time, then we can solve for what's NO2. Or we can go the other way. We can put in the concentration of NO2 and find out what's the rate when the concentration of NO2 is this such and such amount. So there we can find out what that instantaneous rate is at that particular point where the concentration is a fixed number. Now, typically what we do is when we study these reactions, let's change that to A for this reaction. Right. Let's keep it simple. Let's say we're just going to study A and it's becoming something else. Products. Right. What happens in chemistry very often, in the beginning, we've written our equations with an arrow that goes from left to right. But the fact of the matter is, it can go both ways. You can get products returning to reactants. And that's different for every reaction, of course. Some of them, they're so heavily weighted toward products that this one is virtually disappears. So what do we do? Well, if we suspect, or even if we don't suspect, and we just want to eliminate the problem before it even happens, of any reverse reactions, we study the reaction at the very beginning. It's called initial rate. Initial rate experiment. So what do? Well, we set the concentration here, and there are no products. And we study the reaction only at the very beginning, when there's so few products that the reverse reaction is virtually impossible. Okay. And we characterize the reaction at the initial rate position. Okay, that's not to say that we don't also study the reaction through its entire life, but when we want to eliminate that possibility, we go ahead and study at initial rates. Okay, now what's next? If you see a reaction that's written like, well, the one that we were looking at earlier, that one. If you write an expression for that, and we have a K value, which is unique for that reaction, and then we have the concentration of NO2, and then we have this N value. That N must be determined experimentally. It has no relationship at all to these coefficients. If it does turn out to be 2, it's just coincidence. It's not derived from the coefficients. Because we're studying the speed of the reaction here, and this is more of an equilibrium situation where everything's in balance. Now, I'm going to show you in a few slides, not right away, but in a few slides, there are circumstances in which you can use the coefficient to determine the N, but not for the overall reaction. This is overall reaction. What we're going to get into in a few minutes is these reactions rarely occur in one step. From here, bam. They usually occur in 2 or more steps. We call them elementary steps. Now, for those elementary steps, you can infer order of the elementary step from the coefficients. Okay, just to give you a heads up for where we're headed. But for the overall reaction, you have to determine this value experimentally. So that means that we've got to figure out how to do that. All right. There are 2 ways to write the rate law. So for anyone who's had a little calculus, hopefully will remember the difference between differential and integral. Differential calculus goes one way, and integral calculus goes the other way, goes converse, backwards. Differential rate law is the one we just wrote, right there. That tells you the rate. It's like this. It's like dA versus dt would be the differential expression for our rate, or delta A over delta T. The integrated rate law goes one step further. It incorporates changes in concentration, not just concentration at one time like this one. That's instantaneous right there. But if we integrate the law over a band of concentrations, then what we can do is incorporate a before and after concentration into the expression, and then it becomes easier to solve the equation. It's more useful. So we have these 2 versions, the differential rate law and the integrated rate law.
Thank you.
Okay, this slide is just a summary of what we've talked about so far. All right. Let's see. Okay. I don't need to say that again. Okay. One of the values of having the rate law accessible and understanding the overall rate law is very often it gives you insight and help in trying to tease out the elementary steps of a reaction. Let's see. So here's one of the most common methods for determining the rate law, that the order of the reaction. Let's see. Okay. I don't have an example in here. The examples are in the review document. I should have put an example in here, and we may do one. But let me just say this. This overall, the general approach to the method of initial rates is to conduct the experiment several times. So you'll have experiment 1. Well, however many you need. And what you do is, if you have more than one reactant, well, you can do it with one reactant, of course, but if you have more than one reactant, you would say initial concentration, right? We put that 0 there. That little 0 means that's at the very beginning, time 0, we start. And if we say, let's start off with this one at 0.1 molar. And we make this one 0.1 molar. And then you determine the initial rate. What's the rate at the very beginning? Right? And you may find something, I'm just making this stuff up as I go along. You may find that the rate is 0.01 molar per second. That's how fast the change is made. And then you may do this one and change this one, but you leave this one the same. And you find that now the concentration, the rate of the reaction changes 2 molar, 2 molarity per second. And then you may take this one back to this one here, and then make this one 0.2. Okay? And this one, it turns out, the reaction rate doesn't change. Okay? So that's the general theme. But you hold one of them constant, like this one and this one don't change. So we're really focused in on that one to that one change. It went from this one to that one. It didn't change at all. So apparently it's not dependent at all upon the concentration of B. That's one type of reaction. But if we hold this one the same and let that one change, then we find out that if we double this one, we double that one. And that's another type of reaction. Okay? So that's where we're going next. I'm going to describe the how to distinguish those different types from the raw data. But that's the overall feel of an initial rates experiment. Okay. In this case, we're writing a rate law for a reaction which has two reactants, A and B. In this case, the rate then is the rate equal to the rate constant times the concentration of A to its order, power n, and times B, concentration to its order, power m. So each one has its own order. This is the order of A, order of B. The overall order of the reaction is just the sum of those two. So if A was order 1 and B was order 2, the overall order would be 3. Okay? That's pretty simple. We have to figure out what that order means, though. You know, what does it mean in practical terms? And that's coming up. So this is just to check. How do those orders, rate orders, compare to the coefficient and balanced equation? Not at all. They're not related. And this is sort of an explanation. The balanced chemical equation is really an expression of stoichiometry. That is, you got so much of this, you should expect to end up with so much of that. It doesn't say how you get there, which is, in our study today, the rate at which it happens. And is dependent upon the mechanism. That is, does the reaction proceed through step 1, 2, 3 before it gets to the end? Or does it just go 1, 2 over here and then go down? Or a few reactions are single step. They just go bam, bam. That's it. So the mechanism has a bearing on the rate of reaction. And we're going to look at that too. Okay. So now we're going to talk about how to distinguish orders of reactions. There can be a whole host of orders of reactions. I mean, if you have one reactant, or if you have two reactants, it gets complicated. If you have three, it gets really complicated, higher orders. So what we're going to do is focus on the three most common orders for individual reactants. So in that case, we're saying this reaction is only A yields products. That's it. That's the only reactant. So what does that mean? Well, it has to decompose into products, or it has to change some way, but we only have one reactant that we're focused on. Okay, so the first type is zero order. So in zero order, and let me do it this way. I just added a leaf to my board. Be sure it's, oops, nope. Shoot, I can see everything. There we go. Everything's on board. We used to have this dinner table when I was a kid, and they still make them. And you unlocked the thing underneath it, and you pulled it apart, and you stuck in a leaf, they called it. And if you needed more, you spread it some more and stuck in a second leaf. So I've added leaves to my board. So zero order, that we would say is, well, we'll just write it. Zero order. Is an expression of the rate that looks like this. Rate equals K, right, to the zero order. Right? That's it. I mean, if we're going to say it's zero order, then that n has to be 0. But what does that reduce to? Right? In terms of mathematics, anything to the 0 power is 1. So the rate is simply equal to the rate constant. Okay? So what does that look like? when we graph it. Okay, if we have time and concentration here, let's see, A, like that, then over time, the rate never changes. It's a straight line. So as A is disappearing, it disappears as at a constant rate all the time. It doesn't matter what your starting concentration is. It'll always be a straight slope. That's zero order. Now, the integrated rate law, we'll look at it this way. If you graph it that way, then what's the y-intercept? If this is time zero, then the y-intercept is the initial concentration. That's where you start, right there. Right? So the y-intercept we know is this. Okay? I'm building the straight line formula backwards. You know, y equals mx plus b. That's the b, y-intercept. And then the k times time is the slope minus k, right? It's a negative slope, so it has to be a minus k. Okay, and the actual concentration anywhere along that line is that. So that's your integrated rate law, where you have initial concentration, final concentration at any time t can be determined from that formula. That's the equation of this line. Okay. Stop me anytime. You know, if you need to, if you need clarification or you just need a breather. I know this is a lot to take in. Kinetics is not an easy topic to begin with. I didn't mention at the beginning, but we're going to study kinetics first before we study equilibrium. And there's a reason for that. We need to know something about reaction rates for the forward reaction and the reverse reaction, because the balance of those two is where you get equilibrium. So we study kinetics first, then we go to equilibrium. Okay, there's one other thing that can come out of this, and it's in my mind, it's a derivation of nuclear physics. In other words, radioactivity, called half-life. But half-life of the reaction can be expressed in chemistry also. Right, well, there's the slope of the line, and that's an expression of this. So that slope, that k, is actually equal to change in A over change in T. Okay? Now, here's the half-life. I'm not going to derive the half-life. I mean, it'd take too much time. So we're just going to say the half-life for a zero order reaction, let's see, yeah, T1 half. Is equal to the initial concentration divided by 2K. So what does that mean? Well, in general terms, half-life is the amount of time it takes for the initial amount to half disappear. So after that time period, half of this is gone. Okay? And that doesn't have to be a fixed number. You can pick whatever concentration you want to start with as A0 and then apply this K value to find the half-life. Okay, so initial concentration is up to you. Right? We could start this anywhere, right? But eventually, we're going to come up with this equation for the integrated law and the half-life. So what does that mean? What does this expression mean? Well, in these terms, the half-life itself is dependent upon the K value, and it's dependent upon the concentration. So if you double the concentration, you double the half-life. Or if the K value is decreased by a half, then you also double the T because it's in the denominator. So that just says half-life for a zero order reaction is dependent upon the K value and the initial concentration. Okay. Next, first order, right? We've done zero order. Now let's put a 1 up there and see what that looks like. First order. So now rate is equal to K times A to the first. And of course, you wouldn't write the 1 in there. If you leave it there, then there's got to be at least one of them, and 1 is understood. Okay, so what does that look like when you graph it? Well, if you graph just the raw data against time, you get a curve. And that curve varies depending on the reaction, but you don't get a straight line. And scientists hate curves. Any scientist who likes a curve is kind of weird. You know, they ought to be sent to the outer regions, away from normal people. What we like to do in the sciences, if we have a curve to deal with, we want to transform the data in such a way that it gives us a straight line. Because straight lines are so much easier to deal with calculations. So how do we get a straight line out of this one? Well, the way you get a straight line out of that one is to take the natural log of the concentration. So if you got this value for the actual concentration, if you take the natural log of the concentration, natural log, and remember logs have a basis, right? The log is dependent upon the base. Common logs are base 10. You remember the definition of a log. The log of A, base 10, is equal to, let's say, x. What does that mean? Well, that means x is the power of 10 that equals A, right? That's what log means. That's the power of this base that equals that. So for this one, if the natural log of the concentration of A equals something, this base is E. That's a very special number in mathematics. It's an irrational number. It's a non-repeating decimal, 2.3 something, 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 something. It just goes on forever. But this would be E to the X equals that concentration of A. So what we do is take the natural log of A and plot that against the time. So when we do that, now we get a straight line. Okay. So the slope of this line is again negative k. And the expression here, so what's that y-intercept? The y-intercept is not a0, it's the natural log of a0. Right? So now we have all the information we need. Y, or log a, equals negative k times t, here, plus the natural log of the initial concentration. So that's the integrated expression for this differential equation right here.
And how do we get the natural log again?
It's in your calculator. There ought to be a button in there that has a LN. Let's see what it looks like on mine. Mine has a separate key.
I got a log button.
You got one that says LOG?
Yes, sir.
Okay, that's the common log. You need the one that says LN.
The side of it.
Okay, there you go. That's the one you use for this transformation.
Okay.
So you would have a set of data where you have concentration here, and then you would have time here. If you plotted that data here, you get a straight line if it were zero order. If it was first order, then you plot it and get a curve. But if you took this and transformed it like that, and you get another series of numbers and plot these two, you'll get a straight line if it's first order. So now I'm developing also at this time a detective's kit. Right? You want to find out what's the order of the reaction relative to this reactant. You plot it this way, you plot it that way, and you plot it the next way that I'm going to show you, and see which one gives you a straight line. Okay, that's where we're headed. So let me make room for that. I got to finish the half-life first. So what's the half-life expression for first order reaction? Okay, the half-life expression for a first order reaction, well, there's an example, right? So we took the dinitrogen pentoxide concentration and transformed it against time and plotted that and got a straight line. It's still a negative slope, but it's a straight line. And the half-life is dependent on 693 K. Notice what's changed. The half-life of a first order reaction is dependent only upon the K value. It doesn't matter what the concentration is. The half-life is always going to be the same no matter where you look at it as your initial. You could start here, you could start there, you start there, it doesn't matter. The half-life will be constant because this is constant. Okay, that's just the way it is.
So it's always 0.693.
Right, divided by K.
Okay.
Yep. Okay, so now we need to look at, there's a, do I want to do that? Hold on a second. I'd rather go to second order and come back to that other problem, okay? Yeah, let's finish off the discussion of the orders first. So for second order, we have rate equals K, A to the second power. Okay. These are the three main, most common order expressions for single reactants. Okay, so what do we get when we plot time against the raw data for a second order reaction? You always get a curve. If it's second order, you're going to get a curve. Like that. Okay, so how do we fix that one? Well, for a second order reaction, you take the reciprocal of the A values and plot those against time. Then what do you get? In that case, you get a straight line, but now the slope is positive. Okay? So the integrated rate law will look like this. Reciprocal of A equals positive K T, right? Positive, plus 1 over, excuse me, yeah, that's right, 1 over A 0, initial concentration. So that's what the integrated rate law for second order reaction looks like. Okay, so now we need a half-life expression for this one. Sometimes when we're solving problems, the data is easier to, it's easier to tease out these values here, the K's, if you do it from the half-life direction. If we know the half-life is like this, and we can deduce that it came from a second order, first order, or zero order, we know which one to apply. Then we can input half-life and concentration if necessary and find out what the K is from the half-life equation. So you may not have to go from this direction. Sometimes it's easier to go that way. Oh, but the half-life expression for second order is 1 divided by K and initial concentration. Okay, so that means that second order also depends upon the concentration of A0, the initial concentration, plus the K. Another thing I might point out is all three half-lives are dependent upon K, the reciprocal of K. It's in the denominator. K, K, K. This one has A0 in the denominator. This one's in the numerator. That one doesn't have it. Okay, so sometimes you can use that difference. If you know different, if you know have half-life data, say at this concentration, when we take the concentration down to here, half-life changes, take it down to here, it changes again. You can do those comparisons and often use that to determine if it's first, second, third, or zero first or second order. Okay. Okay, so now let's go back. Yeah, let's go back to that problem that I skipped. There it is. Okay. I'm going to have to erase this. Well, maybe not, because I've got it all worked out on the slide.
I wrote it all down.
Okay. I'll erase it when I have to. This is just a sample problem to try to orient you to thinking in terms of reaction orders and half-lives and so forth. Let's say the first order reaction is 35% complete at the end of 55 minutes. What's the value of K? All right. Yeah, I'm going to have to erase it. All right. So this is a word problem, and word problems are purposely designed to confuse. So let's extract the information from the word problem and put it on the board in a way that's more understandable. We're looking for the value of K. That's the end game. What's K? But what are we given? We're given it's a first order reaction. Okay, we know that. And it's 35% complete after 55 minutes. In 55 minutes. Okay, so what does that mean in terms of actual concentrations? Right. If it's 35% and we're talking about disappearance of reactant, so if we start off with this, what is this after 55 minutes? Right. Relative to this, after 55 minutes, how much of that do you have left? You've actually got 65% left, right? Because it says it's 35% complete. That is, complete means all of that is gone. So if it's 35% complete, you've still got 65% of it left over, don't you? So that means this would be 0.65 of that after 55 minutes. Well, actually, that's not right. Excuse me. This equals 0.65. There. That's true. This is equal to 0.65 of that after 55 minutes. Okay, so that's everything that we're given. And they want to know what K is. Right? So we're told that it's first order, right? So we know the reaction equation for first order is going to be this one, right? And we know that the rate law is going to be this one, K. Like that, first order. But the integrated rate law is this one, right? First order is always natural log of the concentrations. Okay, so the reason that this one is being manipulated in this fashion is to make this ratio down here. This one divided by that one is equal to this, right? Look at that. If this is equal to 0.65 of that, then this divided by that, right, bring it over here, is equal to 0.65. Okay, so that's why we're manipulating this equation to give us that ratio, right? Because that ratio we do know. We know this ratio. So if we reduce this first order rate law equation down to here, we know that E is a constant. T, we know, is 55 minutes. And minus X is the unknown that we're searching for. So how did we get there, right? Well, the log of A minus the log of A0 is the same thing as the log of the quotient, A divided by A0. That's just a mathematical transformation that's was proven in your algebra class. Okay, that transformation is that's the way logs behave. So now that we know that the log of this equals that, we know that this base E to that power over here is equal to this expression. Just like I showed you earlier with what does a log mean? We're just converting this log into this exponential expression, which is the equivalent, a derivation of the log expression. So now we have that to go on. Now what we do is we substitute 0.65 for this quotient in the equation, and we find that here's 55. Right? And now we can solve for K. Right? So, and that, let's see. Now that we have these values in here, how do we solve that equation for e to a power? We just take the log of both sides. Right? The log of this side is equal to the log of that side. And then the log of e to a power, the natural log of e to the power, is just the power. So now we've got the log of 0.65 equals minus k times 55. And we get k on one side. And now we know that k is 7.8 times 10 to the minus third. Minutes, probably reciprocal minutes, isn't it? Yeah, reciprocal minutes. So we used the expression here to determine what k was. I know that's a lot of steps and it's kind of maybe hard to follow, but I think if you sit down and study it, that it'll become clear that I haven't cheated anywhere with my math. Okay. Now we got the zero order, first order, second order under our belts. You want me to switch? Are you ready? These slides are in Blackboard too. Okay, everything you see up on these slides is in that version in Blackboard. You just need PowerPoint to view them. Okay, there's a second. We did that already. Okay, let's see. How am I doing on time? Are you supposed to have your doctor's call?
Right here in a minute, yeah.
Okay. Oh, they're going to call you, aren't they?
Yes.
Okay. I'll just keep talking. Let's see. Okay. I've got a little bit to go, so I'm probably going to run past my 3 o'clock limit anyway. And if we were actually sitting in class, well, you know this from experience. If I have a lecture and we haven't scheduled a lab that day, I'll just bleed over into the lab time and finish the lecture. So just think of it in those terms, and that's what I'm doing. Okay, so for this example, we have A that is being changed into some sort of products. Our initial concentration of A is 5 molar. And the first two half-lives are 25 and 50 minutes. So like I said before with word problems, let's put it on the board and try to blow away the blue smoke so we can see the actual problem. Initial A0 is 5.0. 5.0 molar. Right? And this is, let's see, concentration of A. And this is at time 0. Okay? Time 0 in minutes. And it says the first two half-lives are 25 minutes. So the first half-life is 25 minutes. So after 25 minutes, half of that is gone. Okay? The second half-life is 50 minutes. So after 50 minutes, this much is half gone, right? Now we're starting at a new A0. So for this half-life, it starts from here. From this half-life, it starts from there. So after 50 minutes, oh, excuse me. Yeah, that's wrong. That length of time from here to here is 50 minutes. So what is T? 75 minutes. Okay, so at 75 minutes, we have another half-life, right? 50 minutes here. And now this is 1.25 molar. Okay, there you go. So we want to write the rate law for this reaction. And you can write a placeholder rate law, which would be the rate equals K times that to the N. We need to know what N is. We need to know what K is. Calculate the K. Okay. So in order to calculate the K, we could use the half-life formulas if we knew whether it was 0, first, or second order. Okay. So can we eliminate one of them? I mean, right now we got a 3-to-1 chance, a 1/3 chance of getting the, not 3-to-1, 2-to-1. We got a 1/3 chance of getting the right one. Can we eliminate one of them? Right. Well, does the half-life depend upon concentration? Right. If it depends on concentration, then it's 0 or second order, not first order. Remember, the half-life for second order was 0.693 divided by K, independent of the concentration. So it looks like if the concentration changes, you get a different half-life from 25, and 50, depending on different concentrations. So it's not first order. It's either 0 order or second order. Okay? That's what this is saying. And that initial observation saves you a lot of work because you eliminate one of them already. You need to just find out, is it the first or the second? If the rate law were 0 order, then the half-life would be concentration of A divided by 2K. Right? So if we do it that way and say initial concentration divided by 2K takes 25. Right? So 25, starting at initial concentration 5, leaves us with K unknown. Right? One unknown. We solve for K. Right? So we take 2 over here to make 50. And then we take K over there and put the 50 back. That's what we did over here. 5 divided by 50 is 0.1. So in this case, K would be 0.1. Well, K is a constant, right? So if we do it for the next one, right, where we have 50 as our half-life, and now we're starting at 2.5. We've moved down to this one, 2.5, and solve for K, we get 0.025. That can't be it, because the K is a constant, right? K can't change. So that means that 0 order is out. 0 order is wrong. So it has to be second order. So we go to the half-life for second order, 1 over K times the initial concentration. And we do the same concentration analysis here. Put in the concentration against the half-life, solve for K, put in the concentration for the second half-life, solve for K, and they're the same. 1 divided by 125, and turn that into scientific notation is 8 times 10 to the minus 3. Okay, so that's where we used half-life information to find out what K was. Now you can put it over here. We can make this rate equals, what's K? 8 times 10 to the minus 3. And then times A to the what power? To the second power. Right? That's our rate law. I think it asks us for something else too. Let me see. Calculate A at 525 minutes. Okay. So how are we going to do that? In order to do that, we need the integrated rate law. So the integrated rate law for second order is 1 divided by A equals K times time plus 1 divided by A 0. Okay? So we know what K is right here. So we just plug K in here. 8.0 times 10 to the minus 3. And then I got a noisy cat. Okay. So now, if T is 525 minutes, then we just pick our starting point. It says after 525 minutes means we're actually starting from 0 again. So our initial concentration is 5, right here. And this is our unknown. And there's our K, and T would be 525. So now we have an equation in one unknown. We say divide 1 by 5 is 0.2. And then multiply this times that plus this, and then take the reciprocal. And you got A. I think I got that all, let's see, in nauseating detail here. There you go. So there's your KT, and there's your one reciprocal of A0, and there's your value. 0.23 minutes, molar. So starting with 5 molar, after 525 minutes, you're all the way down to 0.23 molar of A. Okay? Let's see. I'm going to keep up with my hard copy here too. Right. Now, I think I've got coming up a video that was written in Adobe Flash, which means it won't work anymore because Adobe crapped out on us. Oh, maybe, no, there it is. Yeah, so that video is gone. I'm going to have to replace it with something else written in HTML or maybe Java or something like that, or just put a link into a web link for a video. I got to go back and figure out what video that was. I can't remember. Okay, how can you tell the difference among zero first and second order rate laws from their graphs? I mentioned that earlier. If you graph the data, raw data, and it's a straight line with a negative slope, it's zero order, automatic. And the other two will be curves. If you plot the natural log of the concentration against time, and it's first order, it'll be a straight line with a negative slope. If you plot the data transformed in the reciprocal of the concentration against time, then that plot, if it's a second order, will be a straight line with a positive slope. Okay? Now, as is so often the case, we try to start simple and then get complicated, because the real world is complicated. And besides, I've said it before and I'll say it again, nature just does what it does. It could care less what we think about it. And we devise these theories and approaches, these skills, to try to understand what's going on. So the complication is not in nature, the complication's up here. But many reactions occur with two or more reactants. So when you write their rate laws, for instance here, K times concentration of A to the N times the concentration of B to the M. Power of A, or the order of A, is N, order of B is M. How do you deal with that in an experimental situation? Because we've only talked about now one in which there's only one reactant. Right? So if you get both of these reactant concentrations going at the same time, how do you know which is which? Okay, well, one way to do it is to make the concentration of one of them so high that it effectively stays constant, doesn't change. And that's the way we're going to do our kinetics experiment in the lab, where we have bleach concentration against blue dye concentration. Right? So the initial step will make the bleach so concentrated that you can ignore it. You can treat it as if it's a single reactant rate law. So what does that look like? Well, if the rate is like this, equals K times A to the N and times B to the M. What if we you increase this concentration so high that it remains constant? In that case, now we combine this one and this one over here in what we would call maybe a K prime. It's a K value, it's still a K value, but it incorporates both K and the concentration of B. And like I said, this is so high concentration that it's virtually constant through the reaction. And this is times A to the N. Okay. So this is rate, what would you say? Rate 1. Okay. So then you run the reaction like this, and you find out what the order of A is. And then you run the reaction again, but this time you change the concentration of B, the initial concentration. So now it's a different K prime. So this is K prime 1.
Oh, wow.
There's a more complete discussion of this in the document for the kinetics experiment, the lab experiment. Okay, so you can get a more detailed explanation in that one. This is what it looks like, where you've incorporated B into the constant. Right. So I'm not going to spend a lot of time on that right now, since the lab discusses it in nauseating detail. All right, so let's move on. This is a summary of everything we've talked about so far about the 0, first, and second order rate laws. Just compiled right there in one place. This came out of my textbook, chapter 12. I'm not sure what it would be in your textbook, chapter 14. But my guess is that there's a similar table there in your in Brown's. I forget the name of the textbook. Chemistry. Let's see. No, can't remember the name of it. Anyway, so here's an example. This exercise wants you to postulate the final concentration of a reaction if it were zero order, first order, second order. Okay, so if the starting concentration is 5 and the K is 1 times 10 to the minus 2, and the units can change, right, depending on whether it's zero, first, or second order, then after, calculate A after 30 seconds have passed. Okay, so if it's first order, right, here's our first order equation. There's the K as given with your negative. There's our 30 seconds. There's our initial concentration. And the calculation says that zero order, you still got 4.7 molar after 30 seconds. If it's first order, we do that same calculation, only this time with natural log of A, because it's first order. Plug in the same numbers, and now if it's first order, you end up with only 3.7 molar. Okay, so it looks like the trend is shaping up. The higher the order, the faster the reaction. Do the same thing with second order, right? So now you got the reciprocals. Plug in the same K, plug in the same time, plug in the same initial concentration, and after 30 seconds, you've only got 2 molar left. So that would appear to be the trend. From zero, first, second order, you decrease concentration, final concentration over the same period of time. The only thing we've changed is the order of the reaction. Now let's talk about mechanisms. Like I said earlier, most chemical reactions do not occur in one single jump, one step. Most have 2 or more, what we call elementary steps in their reaction mechanism. Elementary steps. Okay. Now, how do you figure out what the elementary steps are? It's kind of it's almost like a crapshoot. What you try to do is postulate different series of steps that you think might be reasonable. And you set up this mechanism, that mechanism, separate mechanisms. Say, I think it might be this one, this one, this one, or that one. And then you eliminate. You say, this one is stupid. I mean, it's impossible. Can't happen for various reasons. And you keep narrowing it down until you have 2 or 3 to compare. And you say, what does the data say? You know, which one actually satisfies conditions of the real world experiment? Because by this time, you have run your kinetics experiment on that reaction and determined what the orders are on each of its components, right? If it's only one, right, you've got an order for that one reactant. That's the order for the equation, for the reaction. If you got 2, then you have elucidated the order for for both of the reactants, and you have an overall order. And then you propose a mechanism that satisfies that experimentally determined rate law. Characteristic of mechanisms is that the one elementary step usually produces one or more intermediates as products. And then those intermediates are used up in a subsequent step. And of course, in order to satisfy, all of your steps have to obey Hess's law. Remember Hess's law. Since well, Hess's law just says it doesn't matter how you get where you're going. You can go there by several steps. But when you add up those steps, they have to equal the overall reaction. And same thing for the elementary steps. You have to add them up so that they give you the overall equation, the overall reaction equation. If they don't do that, that's the first key to throw it out. If it doesn't satisfy that condition, that's an easy decision. You just throw those out. They don't work. They disobeyed. Okay, so here's an example with pictures. If we say that nitrogen dioxide and carbon monoxide react to form nitrogen, let's see, I say nitrogen dioxide plus carbon monoxide reacts to form nitrogen monoxide and carbon dioxide. So the proposed elementary steps, and actually these have been confirmed. You take two nitrogen dioxides here. There's one. Blue is nitrogen, red is oxygen. Two NO2s, and you make an NO3 and an NO. Right? So there's one of your products right there in that first step right here. But this is nowhere in the overall reaction, so it must be an intermediate. Okay? So what happens to that intermediate? Well, then we react the intermediate with this one, the carbon monoxide. And that generates as a product in that elementary step, it regenerates an NO2 plus a CO2. Okay, so salient points of this mechanism. Step one, you're producing an intermediate here that is consumed in the second step. Right? So that's okay. It comes and goes. We never knew it. We don't even know it happened. We're just proposing it. Here was the one that bothered me initially. We're using two NO2s, and there's only one in the overall reaction. But in the second step, we regenerate that used up NO2. So overall reaction, we only use one. So the rule is, when you're adding equations together, if you've got equal molar amounts of a product in one step and the reactant in another step, they cancel because they're on opposite sides of the arrow. So that's why NO3 disappears from the overall reaction, and this NO2 disappears from the overall reaction, and you're left with this one plus that one yields this one plus that one. Right? So it satisfies that first condition. Add the two reactions, the elementary steps together, and you obtain the overall reaction. Now I'm going to introduce a concept that's important for working with elementary steps. It's called the molecularity of an elementary step. the molecularity of a reaction in which there is only one reactant in that elementary step, like A becomes product, whatever. This is unimolecular. Molecularity. Okay. Unimolecular. It means there's only one reactant. Now, A could be a molecule. I mean, it could be CO2, it could be NO2, it could be N2O5, or whatever. There's just one molecule. These are more likely to occur. Probability says, since there's only one of them, it can change anytime it wants if the conditions are right. Bimolecular says A plus B yields products. This is a little less likely to occur probabilistically, because you got to get these two molecules together with the right amount of energy and the correct orientation, right? They have, if they come slam into each other with enough energy to initiate a reaction, but they're positioned wrong for the bonds to break and reform, then it won't happen, right? They come in like this. Let's see over here. They come in like that, won't happen. They come in like this, it will happen. So probability says that this is less likely to occur than that one. This one is called termolecular. And it is almost impossible to have three molecules come together with just the right energy and just the right orientation to initiate a reaction in an elementary step. Right? So it's very unlikely. Sometimes there's no other possibility. When we're proposing elementary steps for a reaction, sometimes that's the only one that'll work. So we're sort of forced to use it. But we avoid using termolecular because it is so rare. The probability is against you. Now, as far as order goes, this one is first order because there's one molecule. This one is second order because there are two molecules. This one would be third order because there are three molecules. So that's where now we can use elementary steps and the balanced equation that goes with them and the coefficients that go with them to assign orders to those individual elementary steps, not to the overall, but to the individual step. Okay, next concept. The next concept is, what's the rate determining step? It's logical, it's reasonable to assume that if you have two or more elementary steps, they're not all going to happen at the same rate. Right? There will be differences in rate. So one of them is going to be the bottleneck. The rate determining step is the slowest one in the series of elementary steps. Could be the first one, could be in the middle, it could be the last one. You know, it's just the nature of the beast. And that just says that the rate is only as fast as its slowest step. So when you're writing the rate law, you can write the rate law in terms of the slowest step because it doesn't matter how fast anything before it is, or how fast anything after it is, because that step carries all the weight in determining the rate. So that's why elementary steps in an overall reaction sometimes are very elucidating in terms of the reaction rate of the overall reaction, because then you're saying that this one step is what slows everything down to the observed rate. Okay. I've already mentioned this one, requirements for the mechanism. When you sum up all the elementary steps using the rules from Hess's law, then the overall balanced equation must be identical to the sum of the elementary steps. If it's not, you throw out that mechanism. And the mechanism itself, once you apply real numbers to it, must agree with the experimentally determined rate law. Okay, those are two hard and fast rules. You have to meet those rules, otherwise your mechanism is bogus. Throw it out. All right, there's another one that I'm missing. Okay, so let's take this example. We've got this reaction where we have one reactant, right? Dinitrogen pentoxide decomposes into nitrogen dioxide and oxygen. So here's the proposed steps. Step 1, step 2, step 3. Elementary steps. First thing, N2O5 is in equilibrium with NO2 and NO3. And this is a fast reaction. Don't ask me how you figure that out. That's a little beyond me right now. So let's just say, all right, we're given that information. That's a fast reaction. So what does it mean? Well, the way it's written here is it's an equilibrium. It goes backwards and forwards really fast. Right? Could be here, could be here, could be at 50% on one side, 50 on the other. It could be the other way around. It could be most of it on the right. But it's fast, right? So we take one of these N2O5s and we decompose it to NO2 and NO3. And then we take the NO2 and NO3 and they react together to produce NO plus O2 plus NO2. That's the slow step. And it should be slower than the first step. Why? Because it's bimolecular. Now, why is this one? This one's bimolecular too, NO3 plus NO, but it's fast, right? Who knows? Maybe it takes less energy to make this reaction go. It takes more energy to make that one go. So it's slower. But this is the rate determining step right here. Now, what would happen if we tried to add these together to see if it satisfies that first condition? Well, N2O5 only occurs in one place here. Add it together and you only got one. So that won't work. We're going to use rules from Hess's law to make it work, or to see if it works. Right? So if we multiply this one times 2, that gives us 2 N2O5s. We're good there. But that gives us 2 NO2s and 2 NO3s. Well, they're on the right-hand side. Are they going to cancel anything on the left-hand side? Because we can only end up with NO2 and oxygen on the product side. Right? So we got 2 NO2s here and 2 NO2s there and 1 NO2 here. Right? So this NO2 cancels that NO2. This NO3 combines with this NO3 to make 2, but you got 2 NO3s on this side now, so they cancel, right? So those are gone. These 2 are gone. And these are gone. They're on opposite sides of the arrow. So that's good, right? We don't have any of those extra NO3s hanging around because they're not in the overall equation. Let's see if we got anything left. N2O5, NO2, yeah, there and there. O2 is there, okay? Everything that we need is still there. Is it in the correct amounts? All right, 2 N2O5s, good. 2 NO2s plus 2 NO2s, they're on the same side of the arrow, so that's 4 NO2s, we're good there. 1 O2, we're good there. So the first condition is met. Add them all together and you satisfy that condition. Now, what if we write the rate law in terms of this slow step? What would it look like? Remember, now that we have the elementary step, we can use the equation itself to help us write the rate law because this is a bimolecular reaction. But it's not going to do it. Sorry. I thought I had pulled that together. We're going to do it with a hypothetical reaction. Sorry. But you could theoretically write the rate law from this reaction. And if you did, you would end up with NO2 and NO3 in the expression because we're working from reactants disappearing. We're working from reactants, but none of these, NO2, NO3, they don't appear in the overall, right? So we have to modify and substitute so that we end up with N2O5 in our final expression. And that's the type of reasoning that we're going to use in the next series. Okay, for this example, we have this bimolecular, and this is the overall balanced equation. And this is the proposed mechanism. This is fast, and this is slow. A plus B produces an intermediate D that is used up in the second step. So that's good. The D doesn't appear here, and if we add it together, we get that reaction. Now, what's the rate law for this mechanism? We take the slow here, and we write the rate law. Yes, it does meet the first condition. Add them together, and you get the overall reaction. Okay, so if we're going to write the rate law, we write it in terms of the slow reaction. But when we do that, we're going to precede that with some added information. Each one of these rates is governed by its own individual constant and rate law. So the forward reaction in terms of A and B is governed by this K value to produce D. But the reverse reaction is governed by this other K value, which we say K minus 1, which means it just goes to the opposite direction. But those are fast. The slow one is governed by this K2, which only goes in one direction. And that's part of the mechanism proposal, whether it's unidirectional or bidirectional. So if the slow step is rate determining, then the rate should look like this. There's your K2, the rate constant for this reaction. And here is your this is a bimolecular, so it's in terms of powers, first power for D, first power for B. And the overall is bimolecular, right? Add them together, the overall order for this step is second order. Okay, but notice that our rate expression has D in it. We can't have that. We got B there, that's fine, because B is in the original overall reaction. This needs to be in terms of A and B. Okay, so what do? Yeah, what's wrong with this picture? Right, D is not a reactant. D is an intermediate. So with the information that we've provided in terms of these individual rate constants and this proposed overall rate law, which needs some massaging, this is what we do. Since the fast step is equilibrium, the forward and reverse rates are equal. So if we write it in terms of one direction and one the other direction, we can set those rates equal to one another. Okay? So for this step, K1 times A times B, right? That's one of them, order one. But that rate is also equal to the reverse rate, which is D as a reactant to the first order. And its rate constant is K to the minus 1, or K minus 1. All right, so rearrange that, and you get, you can solve it for D. Now, why would we want to do that? So we can substitute it right here in this one, right? We can get rid of the D. If we know an equivalent statement for D is this, and it's got A and B in it, which are both reactants, then we can plug that D into the slow step equation. And this is the beginning of that substitution. Here's what D, the equivalent of D, is inside these parentheses. Then we just resolve it, right? So why can we say it's K times A times B squared? First order in A, second order in B, because we got two B's here, and these are elementary expressions, right? So we can, if there are two of them, we can say the order is 2. We can only say order 1 here. But where did this K come from? Well, it's a combination of this K, and that K. Those are elementary step Ks, and this is the overall K. So we're proposing that the expression for the rate should be first order in A and second order in B for the original equation. Okay, what was the original equation? Let's go back. There it is. A plus 2B yields C. Now, in my mind, it's just a coincidence that the final expression is second order in B, because the coefficient for B is 2, and it ends up here as the order is coincidental. They're not related. Okay, so there's reaction mechanisms. Now, we're going to propose a model, a theory for that will govern reaction rates and explain why some are fast, some are slow, and so forth, and even how to quantify some of the information. This model says, first, in order to react, molecules must collide. They cannot react by remote control or react from a distance. It's like Isaac Newton. He proposed his law of universal gravitation, but it was just a law. He never could come up with a satisfactory theory that would explain why the gravitation worked. Says you have two big masses here, right? And the force between them is proportional to the size of those two masses, plus it's proportional to the inverse of the square of the distance between them, right? So as the distance decreases, the force increases by the square. That's all he could say. He proposed, just for just to pull things together in his own mind. It really wasn't a valid theory. He just called it action at a distance. Which really says nothing. What this model says about chemical kinetics is the collision model is just that. Molecules must collide to react. And they must collide with a minimum amount of energy for the reaction to proceed. And that typically implies a certain temperature. It doesn't have to be a temperature. If you are able to make molecules collide with amount of energy without increasing the temperature, like firing them from a molecular gun, something like that, then you could introduce the requisite amount of energy to make the reaction. But for common chemists like myself and others, that implies temperature. And then the other factor that's important, I mentioned earlier, they have to be oriented correctly. It doesn't matter how much energy you have, if they're not approach and smack at the right angle and the right side of each molecule, then the reaction will not happen. They'll just bounce off. Or worse yet, they might produce a side reaction, an undesirable reaction. That happens too, very often. So we got these conditions. Molecules have to collide. They got to collide with enough energy. A minimum amount of energy we call activation energy. And that implies temperature. And they have to be oriented correctly. So those three items are required for the collision model to explain reactions. Okay, so that activation energy is the amount of energy required to overcome, that must be overcome, excuse me, to produce a chemical reaction. So what does it look like? Well, if we draw a picture with energy on the vertical scale, the y-axis, and the progress of the reaction, right? It's gone so far. On the x-axis, then we may start off here with reactants, and we add energy, right? This is, say, during a collision. Energy is accumulated by the transition state, right? They reach a certain transition state. If they have enough energy, then they'll proceed over the hump to complete the reaction. If they don't have enough energy, the transition state doesn't completely form. Say here, it'll roll back down the hill. Reaction will not occur. So the difference between the beginning energy of all the reactants and the final energy of the transition state, or the activated complex, we often call it, is the activation energy. And then it'll roll down the other side. And in this case, the products have less energy, which adds to their stability, of course. And the difference between those two, starting energy and final energy, is the change in energy of the reaction. Okay? So this is just an artist's rendition of what that might look like, to go from these reactants to these products. Let's see, what else? Okay. I'm just repeating myself here on this slide, not saying anything new. Now, there was research done on this, and an explanation was proposed relative to activation energy by a scientist. His name was Arrhenius. And he proposed this equation. And he said this K value is a constant. And I believe that's the reaction constant, the kinetic constant, is equal to this other constant, which is related to the frequency factor, times E, right, that little special number, to this power, the negative activation energy divided by the gas constant divided by T. Now this T is in Kelvin, and this constant is the one that has joules in it. It's not the liter atmosphere, it's the one with joules. And then this is the activation energy. Well, you know, that's great, right? This is an integrated equation. I mean, this is a differential equation, and they're notoriously difficult to solve. So we need a transformation of this equation into something that's more useful, right? And here it is. That equation can be reduced to this form. Now, I'm not going to do it for you. It just takes a little more time than we've got. But now the natural log of the reaction rate constant, K, is equal to negative activation energy divided by R times the reciprocal of the temperature plus the log of A, that other constant. So notice what we've got here. We've got Y equals M, the slope of the line, times X, which is the reciprocal of temperature, plus B, the log of A. So the y-intercept will give you this value after you change it back to A. And what we would do is plot K values at different temperatures, at least two temperatures. So if you plot the reciprocal of the temperature at which the K was determined and the K that came out of that reaction at one temperature, and then you plot the point for a different temperature, which will produce a different K, right? The rate of reaction is dependent upon the temperature. Based on the collision model, if you increase the temperature, you're increasing the energy of collisions. You're also increasing the frequency of collisions. So if we plot these two, the K against the T, at least 2 points, then the slope of that line is equal to this term, minus activation energy over R. R is a constant. You solve for E sub A, and there you go. You find the activation energy of that reaction simply by performing the experiment at two different temperatures and finding the K at each one. This is what it would look like. Right, if you plot those, these are several temperatures actually, right? 1, 2, 3, 4, 5, 5 temperatures, which is better because you get an average, a best fit line. Okay, let's see how we're doing. I'm past 3 o'clock, so let me see how many more slides I got to go. Not too bad. Okay, I'll keep going. We'll finish it today. Okay, I've heard this one from middle school because I was interested in sciences back then anyway. But I've heard this rule of thumb that for every 10 degrees, actually the first time I heard it was 10 degrees centigrade in those days. Now it's 10 degrees Celsius. This says 10K, right? It means the same. If you change the temperature 10 Celsius, you've changed it 10K, because the size of the degree in Celsius is exactly the same as the size of the degree in Kelvin. So an increase of 10 degrees doubles the rate of a reaction. Now, what's wrong with that statement? Well, it's a rule of thumb, right? It's a generality. And depending on the reaction, it could be a rate doubling for every 15 degrees or rate doubling for every 8 degrees. Okay. But what we're going to do now is we're going to solve the equations, Arrhenius equation, to determine what would the activation energy have to be for a reaction in order to produce a doubling of rate if we change the temperature from 25 to 35. Right? It might be different if we went from 15 to 25 or from 35 to 45. But for 25 to 35, which is in, it's a little warm for me, right? But it's tolerable. What happens to the reaction rates? Now, this is purely on a chemical basis. Right? For living systems, this rule works as long as the enzyme system that controls the reaction in the living system is not exceeded. Right? If you go too high in temperature, then you run the risk of denaturing the enzyme, and then it doesn't work anymore. And your reaction rate goes like that. So enzyme-mediated reactions are very sensitive to temperature. And they don't necessarily follow this trend, but this is a what if question anyway. All right, so how would we approach that? Well, first of all, we need degrees K, right? So we're actually going from 25, which is 298K, to 308K. Okay, that's first. We need that difference in temperature. And actually, we're going to use the differential rate law for Arrhenius. And I'll show you why that works better, because the first K is at this temperature, that temperature. Okay. The second K is at this temperature. But that K, the second K, is equal to twice the first K, right? That's initial condition. So that means if you take the ratio of this K to that K here, then you get this one, because we substitute 2K for K2 right here. Then the K1s go out, and it just becomes 2. And the A's cancel. So now what do we have? We've got a power of E here with one temperature and activation energy, and we got a power of E here with the same activation energy, but a different temperature. So how do you resolve that? Well, as it turns out, this power in the denominator is the same base as this one. So we can combine the two. We just have to combine the powers. Right? So what does that mean? If you have, let's keep it simple. If you have 10 here and 10 here, and you have this one and this one, what does that mean? That means 10 to the minus 1. Why? Because in the denominator, you take that into the numerator, it becomes a negative. You subtract 3 from 2, 10 to the minus 1. We do the same thing here. We say, if we're going to combine these two, then now it's E with the numerator minus the denominator power. So if it was a minus to start with, now it's a plus. Okay, so now we just need to resolve it, right? We factor out this value here. We can factor out if we factor out the negative of a positive, that makes the expression that's left over negative. That's why you see the negative here. So now we have the reciprocal of T2. We took the negative out of here and the negative out of there, put it out here. Now we have 1 over T2 minus 1 over T1. Still in the power, right? We're not done yet. So now we have this expression, and what we've gone is from here to here. We just take the log, the natural log of both sides. So now we have the log of 2, the ln of 2, and the log base e of e to a power is just the power. So that's why the log of 2 is this one divided by that one times this one. And now we just move that r over here. Okay? Now we're also going to keep this one on that side and put this one over here in the denominator, like that. But we're also going to move the negative, right? So if it's negative on this side, then we put the negative over there also. Now we just fill in the value for r and solve. And it turns out that for that rule of thumb to be true, the activation energy of the reaction has to be 52.9 kilojoules, which is a lot. But that's one of the reasons that food preservation is so effective. If you decrease the temperature by 10 degrees Celsius, which is about 20 degrees Fahrenheit, because the Fahrenheit temperature is a little bit small, it's almost a half. Actually, it's 1.8. So if we decrease 10 degrees, we'll actually only decrease the temperature by 18 degrees Fahrenheit. Then you would reduce the rate of chemical reaction in your food by a half. And if you decrease it at another 10 degrees Celsius, you decrease the reaction rate in your food by another half. So now it's a quarter of what it started at. So you can see where this is going. If we freeze that food and we decrease the temperature by, say, 40 degrees, we've gone through 4 steps, right? We've gone 2 to the 4th power, right? So it's 2, 4, 8, 16. We've decreased the reaction rate in food by a 16th that it would be out at room temperature. And that's also why laboratories that want to preserve biological materials for long periods of time and maintain their viability will freeze them at minus 195 degrees Celsius, liquid nitrogen temperature. Or at the very minimum, 100 degrees, minus 100 degrees Celsius, right? You can initially freeze them with liquid nitrogen. That's good. The faster you freeze, the better. But if you want to store them, minus 100 is pretty good. And there are freezers that operate on the typical refrigeration cycle that will maintain an internal temperature of minus 100 degrees Celsius. I used to operate 4 of them when I was working in research. Well, some of them were minus 100 and some were minus 90. But it was plenty cold to preserve biological samples for extended periods of time, years. Simply because we were reducing the temperature well below the activation energy of the reactions. Okay. So now for one last topic. The issue of catalysts what is a catalyst? A catalyst is a material that has two conditions. Let's see, am I still on board? There we go. A catalyst is any material that is introduced into a reaction that speeds up the reaction It increases reaction rate, but is not consumed in the reaction. Okay? So how does it do that? If it's not consumed, it can go in one end, come out the other, apparently unchanged. The way a catalyst works is that it provides an alternate pathway for the reaction to proceed. So what does that mean? That means that the elementary steps in the reaction are completely different for the catalyzed reaction versus the uncatalyzed reaction. Okay, an alternate pathway. Now, in order for the catalyst to do its job, it has to reduce the activation energy. If it reduces the activation energy, then the reaction will speed up. Why? Because at any given temperature, the activation energy will be exceeded by far more, well, at the same temperature, by far more for the catalyzed reaction than for the non-catalyzed reaction. Right? So what does that look like graphed in terms of the amount of energy that's expressed in the reaction over the progress of the reaction? Well, this purple line is the uncatalyzed pathway. Notice that the activation energy from here all the way up to there is pretty huge in order to produce products. But if we introduce a catalyst, the activation energy is only this high rather than that high. So that means that more of the collisions produce reaction, which means a faster rate. This is another way of looking at it. If you look at the activation energy here, and at the same temperature, you have the same distribution of energies, number of collisions for this reaction, right? It's sort of this looks to me like a chi-square curve. If you've ever had statistics, then you have different shapes of curves depending on the statistical test you're trying to use and what you're assuming about the population. But that's another topic. But notice that the curves are exactly the same for both the catalyzed, the uncatalyzed, and the catalyzed reaction. The only thing that has changed is the position of energy, the activation energy, for the catalyzed versus the uncatalyzed. The uncatalyzed activation energy is way up here, high. So under this curve is an expression of the number of collisions that are in excess or equal to the activation energy. But if you introduce a catalyst over here, then you've moved the activation energy back, and more of the collisions, this part of the curve, have sufficient energy to complete the reaction. Now that's the overall reaction. It's completely different elementary steps, but the overall reaction has not changed. Okay, so what types of catalysts are there? Well, heterogeneous catalysts are those that exist in a different phase from the reactants. So if your reaction is a gas phase, right, and your catalyst is solid phase, that would be a heterogeneous catalyst. Perfect example of heterogeneous is the catalytic converter in your tailpipe on your engine, in the car, your automobile. You have little ceramic beads just packed in there, and coating on those ceramic beads is usually a mixture of platinum and palladium. Those are known as noble metals. Well, the platinum is a noble metal, but they're both very expensive. So that's why they're coated on ceramic beads. You couldn't afford pure platinum beads in your engine, and that would be a waste, right, in the converter, because the reaction takes place on the surface of the bead. So really, you only need a very thin layer. And we use ceramics, of course, because they have very, very high melting point. Right? They can stand very high temperature, and catalytic converters get extremely hot. So as the exhaust from your engine passes through the catalytic converter, the catalyst, platinum or palladium, causes a reaction that should have occurred in your engine to be completed. So you have oxides of nitrogen and carbon monoxide and unburned hydrocarbons. They will complete their reaction. And you still have oxygen there too. Believe it or not, your engine doesn't use up all the oxygen that's available in the air, right? You compress the air with the fuel in the cylinder, and when it is ignited, only part of that oxygen is used. So you still got oxygen in there as it goes through the converter. And the conversion process is completed by a different route. Rather than internal combustion, then a different route mediated by this catalyst provides for the conversion of oxides of nitrogen into nitrogen gas, carbon dioxide, water, and using up more of the oxygen. That's a heterogeneous catalyst. And it occurs on the surface of the platinum by a process called adsorption, not absorption. Absorption is like a sponge soaking up water. Adsorption is a surface phenomenon where various chemicals attach to the surface. And what that does is that brings the reactants very close together at sufficient energy to where they bounce into each other at the proper orientation, the geometry, for the reaction to occur. Okay, that's a heterogeneous catalyst. And it takes place in these steps, right? Adsorption on the surface and activation of the reactants. They migrate on the surface toward one another, and then they convert, and then they desort. Here's an artist's rendition of a catalytic converter. Homogeneous catalysts, on the other hand, are those in which the catalyst is in the same phase as the reactants. And a perfect example of those is enzyme systems in the cells of your body. Those enzymes and the reactants are all in the same aqueous medium. Well, mostly aqueous. They're homogeneous. Another possibility, I'm not sure if it's shown here. No. If you've ever seen, let's see, let me erase this. If you've ever seen hydrogen peroxide decomposing, that's a liquid, and it decomposes into oxygen, gas, and water. Okay, so let me see, how would I balance that? I need maybe 2 here. So that makes 4 there. 4 hydrogens, 4 oxygens, 2 and 2. Okay, so that's balanced. This reaction will occur spontaneously over time. So that hydrogen peroxide you have sitting on your shelf in your bathroom, over time will lose its strength. It'll decompose slowly. But if you want it to go fast and produce a lot of gas, then you need something to speed up the reaction. When you put hydrogen peroxide on your skin, say you've got a cut, every cell has within it what's called an enzyme called peroxidase. That's a catalyst, a biological catalyst, so to speak, and it catalyzes the reaction of this, of the hydrogen peroxide that you pour on the wound and converts it into oxygen and water. Well, one thing microorganisms, particularly the nasty disease-causing microorganisms, they don't like oxygen. Some of them, in fact, are obligate anaerobes, which means any oxygen will kill them, particularly Clostridium or the one that causes gangrene. I think it's a Clostridium too. But that's how you kill those organisms. You convert it into oxygen really fast, makes high concentration quickly, and kills the organisms. But it also irritates your own cells. So you only want to use it initially to clean the wound. You don't want to continue to use it or it'll damage tissue. But that's the biological way. The chemical way is to use potassium iodide. Now, the potassium is a spectator ion. When it goes into solution, potassium just sits there and watches. The real business of catalysis is from the iodide ion. It goes in one end, comes out the other unchanged. But it does provide for an alternate mechanism, which I can't remember right now how that is. But I think it's 2 steps. And it makes that reaction happen really fast. It's best if you use a higher concentration. Hydrogen peroxide on your medicine cabinet is 3%. This works better for show if it's 30%, which you can get over the internet. They'll send it to you. And actually, one of my former students was having a gender reveal party for a soon-to-be-born child. And they had just learned what the gender was. So they got a bottle of, a pop bottle, empty pop bottle, and they poured this 30% hydrogen peroxide into it. And then they put a little dish soap in it to make it foamier. And then they poured color into it. So they poured food dye, blue food dye for the boy, red food dye for the girl, right? So, and nobody could see that until the reaction was started. So the dad, my student, took potassium iodide crystals, a spoonful of them, and dumped it in the bottle and then stood back. And it just shot up. A nice foamy column of, you know, I can't even remember what color it was. One of those colors, pink or blue. And that's how they revealed a gender. But it was catalyzed with iodide ions. Okay. Now, what other types of homogeneous catalysis? That was homogeneous because potassium iodide had to go into solution before it could work. So they were all in the aqueous phase. But this is a gas phase homogeneous catalysis. And this is a bad one. Nitrogen monoxide produced at the Earth's surface by human activity drifts into the upper atmosphere, where we have that ozone layer that absorbs ultraviolet light from the sun and protects us from being burned to a crisp. And it decomposes the ozone by this catalytic conversion. Notice that this nitrogen monoxide goes into the reaction in this mechanism here, and it comes out over here, seemingly unchanged. That means it can go off and do it again with another ozone molecule. That's why it's so bad. It doesn't just react, it's a catalyst. So we destroy the ozone here, and the overall reaction is this ozone combined with this free radical under the influence of NO as a catalyst produces oxygen, right? Diatomic oxygen, which doesn't absorb UV as efficiently. Okay. So this would be a reactant. This would be a reactant. This would be a product. And this is your catalyst right here. If it goes in the mechanism and comes out the other side, then that's a catalyst. Freons tend to do the same thing. Freons are a class of compounds, man-made compounds, that are usually carbon skeleton. Could be just one carbon if it's derived from methane. And the hydrogens around the carbon if it's derived from methane, these hydrogens are substituted with various, usually halogens, fluorine, chlorine. And what happens is, in the upper atmosphere, the UV light causes a decomposition of this, in this case, this particular molecule, Freon 12, and produces a free radical, chlorine atom. Okay. Free radical is any atom or molecule that has an unpaired electron. What that means is the unpaired electron is more reactive than paired electrons. That's why chlorine typically occurs as the diatomic, right? Fluorine is diatomic. Bromine is diatomic. Iodine is diatomic. Oxygen is diatomic. Nitrogen is diatomic. Hydrogen is diatomic. Iodine, no. Bromine, no, iodine is diatomic. But they're diatomic because they have those very reactive free radicals that they would be, independently, they would be free radicals. So they are more stable if they're combined like this diatomic. But when they're like that, they're extremely reactive. And that free radical will react with ozone, decompose it, and it is a catalyst that's produced in the upper atmosphere from the Freon. Now, this Freon is notorious. Freon 12 is probably the worst for doing that. The more complex Freons, which have 2 and 3 carbons hooked together, are less likely to do that. And there are substitutes being developed all the time that are less likely to produce this ozone destroying effect. Problem is, they are more expensive. This Freon is dirt cheap, or it was dirt cheap when it was legal. Okay, let's see. We ought to be getting close to the, oh, we're at the end. And I'm only 45 minutes over. Okay, so next time we meet, next Friday, we'll have a review session on this chapter. And what you need to do to prepare is go to your review document that's in Blackboard. And remember, it's the same format as always. It looks like a test, looks like an exam. And you have one copy that's without answers, one copy that's a key, and then another in my handwriting that is solution to all the problems. So ideally what you would do is you would take the test and find out which ones you got wrong and need work, then go to the key and find out what the answers are and figure out, you know, how did I get this wrong? And work on that until you get those right. And in the process, if you determine that you just can't figure it out, you know, you don't, just the light bulb hadn't gone on, then go to my worked problems and see how I did it. At least that's one way to do it. There's usually more than one way to solve a chemistry problem, but that's one way that I did it. And see if that helps you understand why the answer is the one that's given. And then that way you can eliminate all the problems that are solvable by yourself, and then you can bring the ones that you just still can't get, bring those to our review, and I'll help you with those. As is my custom, when we first start the review session, I open the floor to any problems that you have, so be ready, and you can get your problem worked on first. And then if we have any time, I'll go back and just do a general review. Okay, so that's it for chemical kinetics.